This video is an introduction to sections 12.4, 12.5, and 12.6. You should read through the material in these three sections on your own. A lot of it should be familiar, and I'm going to point out a few things in these three sections which may be new. So, for position, we have the vector r, which is going from the origin to the object's current position. Sometime later, the object is at a new position. This is r prime, and we find this vector delta r, which is pointing this way, by doing r prime minus r, or you could say r final minus r initial gives you delta r. And for the average velocity, we have delta r over delta t. Remember, velocity has magnitude and direction. And we get the instantaneous velocity by taking the limit of delta r over delta t when delta t goes to 0. Okay, now we also have s, which is the path function for the object. This perpendicular line here shows when s is equal to 0, and s is measuring the distance that the object travels along this path. S is not a vector. And if you want to know the speed of the object, which here this is a bold v for the velocity vector, the magnitude of the velocity vector they indicate with this v here, which is not bold. And so this is the speed, which is a scalar quantity. Oh, sorry, you couldn't see that there. Okay, so this v is a scalar quantity, and it's the derivative of s with respect to t. That gives us the speed of the object. Okay, you get to read through that page on your own, you get to read through the next page on your own, and that brings us to section 12.5, where curvilinear motion for rectangular components is discussed. The notation is slightly different than what you saw in Physics 261 if you used spiral physics, but the basic idea is the same. So we have the vector r, which is a position vector. It's in 3 dimensions. And it is x I hat plus y j hat plus z k hat. Remember that oftentimes in textbooks, rather than putting an arrow over a vector like for the velocity here, when we write it, that would be v with an arrow on top. In textbooks, often they make it bold instead of putting either the arrow on the top for the vector or the hat on top for the unit vector. So we have our position vector here. In Physics 261, we had a similar position vector, only we wrote it as rx I hat plus ry j hat plus rz k hat, and usually it was only in 2 dimensions. Okay, and then oftentimes in Physics 261, we had to find the vector r hat, which is a unit vector pointing in the same direction as the vector r. So in order to do that, we found the magnitude of this vector. So the magnitude of the vector would be, with this notation, x squared plus y squared plus z squared to the 1/2. That is the magnitude of the vector r, which also we could write like this, but we don't always do that. So you could say just r without the arrow on top to show that it's the magnitude, or if you want to be really clear about what you're doing, you can say the magnitude of the vector r like this. So in Physics 261, that was rx squared plus ry squared plus rz squared to the 1/2. And then, do you remember how we found the vector r hat? That would be the vector r divided by the magnitude of the vector r, or rx I hat plus ry j hat plus rz k hat divided by rx squared plus ry squared plus rz squared to the 1/2. Okay, now in the textbook, they do not call this r hat. So I hat, j hat, and k hat are still I hat, j hat, and k hat in the textbook. But for other unit vectors in this textbook and in a lot of upper level engineering and physics textbooks, you're going to use different notation, and we have the letter U, so it's bold, so you know it's a vector, and U tells you that it's a unit vector. So we had R hat, now we're going to use R as the subscript, so we know it's a unit vector, and in the textbook it's just in bold, but I should put a hat over it. So you know it's a unit vector because you use the letter U for it, and you know it's for R because of the subscript. Okay, so that's standard notation in many upper level textbooks, as I mentioned. You also might see in some textbooks, instead of U being used, U presumably for unit vector, you have an E, so that would be E hat R, where the E is for Einheit, which is German for unit. Okay, so we will often see the U when we have a unit vector in this textbook. And oh, the other thing, we already know how to take the derivative of the position to get the velocity. We take a time derivative here, so the velocity would be the derivative of x with respect to t. That gives you the x component of the velocity. The derivative of y with respect to t would give you the y component of the velocity, and similarly for z. In Physics 161, you may have seen that as the x component of the velocity is the derivative of Rx with respect to t. Okay, but we could also write this, instead of dx dt, we can write that as x dot. So x dot means the derivative of x with respect to t. Whenever you have a dot, it means take the derivative with respect to t. So you can combine some equations that they have on this page to say the velocity is the derivative of x with respect to t in the I hat direction plus the derivative of y with respect to t in the j hat direction plus the derivative of z with respect to t in the k hat direction, or you could write it as x dot I hat plus y dot j hat plus z dot k hat. And you could also say the velocity is the x component of the velocity in the I hat direction plus the y component of the velocity in the j hat direction plus the z component of the velocity in the k hat direction, which means that Vx is equal to x dot, which is the derivative of x with respect to time. Okay, so that's just putting together some of the equations that they have on the page there. Similarly, for the acceleration, the x component is the derivative with respect to time of the x component of the velocity, which means that it's the second derivative with respect to time of x. So if you take two derivatives with respect to time, then it's x double dot. So let's just write that out. X double dot would be the second derivative with respect to time. Okay, so the dot is always for a derivative with respect to time, unlike a prime, which could be a derivative with respect to something else. Okay, we have similar equations for the acceleration as we did for the velocity. So, of course, the x component of the acceleration would be the time derivative of the x component of the velocity. Okay, so I don't think I need to say anything more about that. Whenever they give you a blue box, I would pay special attention to what's in the blue box and also pay attention to what's in the green box here when you read through this section on your own. That brings us to section 12.6, which is for projectile motion. If you look on your equation sheet, you have equations, which we talked about, I think, when acceleration is constant. So we have these three equations here, which you can use for projectile motion. So that's basically what we have here. They give you some for horizontal motion and some equations for vertical motion. So for projectile motion, when an object is falling under the influence of gravity and there are no forces other than the gravitational force acting on the object, or if there are any other forces such as air resistance, they're negligible. Then the acceleration in the x direction is 0. So that's what they're showing you here. If the acceleration is 0, then you get this for the x component of the velocity. Acceleration is 0, so we get this equation here. And same thing for that equation there. In the vertical direction, the acceleration is pointing downward and it is equal to g. And we are either going to use 9.81 meters per second squared for g or 32.2 feet per second squared. If you haven't used the 32.2 feet per second squared for g before, you might want to add that to your equation sheet. And we are going to use 3 significant figures for g, so maybe you want to add the 9.81 meters per second squared to your equation sheet. Also, if you are unfamiliar with the last significant figure here being 1. And so we can say the acceleration is equal to negative g for these equations to get what they give you here. I probably won't be using those equations too much, and if I do use those equations, I would prefer just to get them from the 3 equations that we have on the equation sheet. So it's not too hard to arrive at these equations just by putting in the acceleration that we have. There's a nice little figure here that you can look at. Basically, it's showing you that the acceleration in the vertical direction is the same for the 2 balls, even though the yellow ball has been given some initial velocity in the x direction. Okay, and it looks like that concludes the reading material in section 12.6. So now we are going to go ahead and look at some example problems. I will say this, the way that I will be solving projectile motion problems, which if you took Physics 161 with me, you'll be familiar with, is not the same way that they will be solving the problems in the book, but I think it would be good for you to be familiar with both ways of solving projectile motion problems. So you may want to read through the example problems that they give you here, but just know I'm going to be giving you another method for solving projectile motion problems. But if you took Physics 161 with me, then you'll already know what it is. Okay, so that's coming up in our example problems.